Right, let's get started. So this is the probabilistic inference session. We're going to have 3 talks. If you guys are ready, we could have a seat and get going here. So it's my pleasure to introduce Hugo Paquet. He's going to be giving a talk on affine monads and lazy structures for Bayesian programming.
Sounds off. Okay, thanks. Yes, thank you. So, this is joint work with Swaraj, Younesse, and Sam at Oxford. And it's about probabilistic programming with lazy structures. I can't. So we like probabilistic programming because it's a nice language for describing distributions and measures. It's a nice practical way to do measure theory. And this is very well understood in a kind of finite dimensional setting. But in this work, we've explored how well it can work in an infinite dimensional setting. So in statistics, this is called non-parametric sample spaces. And so the point of this work is to show that in this non-parametric kind of settings, a lazy programming style is very natural and very useful. And so we demonstrate this using monadic metalanguage, which is a kind of theoretical lambda calculus with monadic operations, which is intended to be lazy. So we then look at adding lazy structures like streams and infinite trees and so on to the language. And we've implemented it in Haskell, so we get this prototype probabilistic programming language called LazyPPL, so lazy probabilistic programming language. Okay, now I'll show lots of examples from statistics to illustrate. Right, just to summarize the key idea, if you're doing lazy probabilistic programming in this monadic style, you should really have 2 separate monads. So on the one hand, you should have a probability monad, which is used to build probability distributions. And on the other hand, you should have a measures monad for building general measures, so possibly un-normalized measures. And this is where inference happens. And the reason you need to keep them separate is because in this context, in this lazy context, the probability monad necessarily has to be lazy or affine. I'll talk about what that means. Whereas the measures monad is necessarily non-lazy or non-affine. So in other words, if you know what that means, sampling has to be lazy, whereas scoring has to be non-lazy. Okay, so in the talk, I'll first just talk about prob, and I'll talk about interactions between laziness and probability. And I'll illustrate this with some examples. And then I'll add the measures monad, and we'll look at inference, and I'll discuss the semantics, because actually a lot of this work is inspired by the denotational semantics of probabilistic programming. And I'll explain the implementation in Haskell. My first example is a fundamental process in probability theory called the Poisson process, and here it's implemented in a lazy way. So the Poisson process is an infinite, or say a random infinite set of points on the positive real line. You can do it on other spaces too, but in this case, in the positive real line, the way to implement it, or the way to simulate from a Poisson process, is to start from 0, sample a real number from an exponential distribution, record that point, and then do that again and again. And so you're sampling the step sizes, and this way you're recursively, lazily producing an infinite set of points. This is the implementation in this kind of Haskell-style syntax. So the Poisson process is a program of type prob of lists of reals. And here, lists is really to be interpreted as infinite, or at least possibly infinite lists, like in Haskell. And I'm using this do notation for kind of effectful programming. So here what happens is we sample the step sizes, IID from an exponential distribution. So IID means independent and identically distributed. So we have this infinite stream of samples, and then we do some processing to add them up and get the actual points. Right, so I want to take this example a little further and see how we can use the points from the Poisson process as change points in a random piecewise function. So here, the points are random. The change points, the blue points are random. And then on all of the intervals, I sample a function, here a linear function, from some other distribution on functions. And so I get a random piecewise linear function. So this is some implementation for this. The type is that it should take a distribution on functions, and it returns another random function of the same type. And the program is very simple. It's just you sample the change points from a Poisson point process from the previous slide, and then you sample the pieces, so the little individual functions, IID, from the input distribution on functions. And then you do some splicing, so this is some external function to produce the piecewise function. Right, so if you call this, of course, if you call it many times, you might get completely different functions, because every time we're changing the change points and changing the pieces as well. But what's really interesting is that actually when I call this program, because it's all lazy, I haven't actually computed anything, so nothing's really happened. So it's a function, but it's a lazy function, so we don't do anything. And the computation really only happens when I try and use f. So for example, if I try to apply f to an argument, or if I try and plot it, and so if I try and evaluate f at the value 4, for x equals 4, actually what's interesting is that the number of variables I need to actually sample in order to compute that value, f of 4, is unbounded. That's a well-known property of the Poisson process, that for an interval, for a fixed interval, the number of points that land in the interval is always unbounded. So in order to compute the f of 4, it needs to figure out the change points, sample the functions themselves, and so on. But even though this is unbounded, you can't really see that at all in this program, because it's all handled completely implicitly with the Haskell laziness. And so this is an argument why lazy probabilistic programming is very natural for this kind of infinite dimensional model. Okay, this is a summary of our metalanguage with so far just the prob monad. So the basic features are just the standard features of a monadic metalanguage. So it's a lambda calculus with sort of bind and return, and I'm using do notation. And then we add some constants for probability theory, for example, a type of reals. We should probably have positive reals as well. And then some distributions, like the exponential distribution or the normal distribution. Although actually all of these you can encode them using just a uniform distribution if you have enough functions. And okay, there's a whole equational theory that comes from being a monadic metalanguage, but here we add some equations that we specifically want the probability monad to satisfy. These are commutativity, so I can reorder the lines of a program. This is Fubini's theorem in probability. And this affine property, which says that if I sample x from some probabilistic expression, and then I return without using the value of x, then I might as well not have sampled the x in the first place. And I'll say a bit more about why this is related to laziness in the next slide. I think maybe this is well known. But I just wanted to point out that a lot of this comes from or is related to work on categorical probability theory. So in category theory, a monad is affine if it satisfies this property. T of the terminal object is terminal. And one example of this is any probability monad, because a probability distribution on a one-point space, necessarily there's only one of them. So it's itself a one-point space. And people like Tobias Fritz or Paolo Perrone have worked out this definition of Markov category, which is supposed to be an abstract axiomatization of all of probability theory. And they define it to be a symmetric monoidal category in which the monoidal unit is terminal. What that means is exactly these two equations should hold. So monoidal categories have this commutativity property. It's called the interchange law. And then the monoidal unit being terminal means there's only ever one program of unit type. So it has to be the return on the right. So having a construct like IID in the language is kind of and being able to do things with it is kind of the essence of what laziness is about. And I'll try to say why an affine monad is what you need to be able to program with it. So we've added some streams or infinite lists in the language, and IID has this type. And it satisfies this kind of recursive equation on the right, which says you can take the first, to produce an IID sequence, you just sample from the distribution and produce an IID sequence and append them. But imagine I want to use an IID sequence for some distribution P, and I want to say take the first 5 elements of it, what I can do is use this recursive equation to just unfold the program like this. But then I still have this IID line, and I can only remove this because of the affine property of the monad. Okay, so this is, I don't know if this is well known, but it explains why the probability monad necessarily has to be affine. Otherwise, we can't do anything. Right, so I'll move to the second part of the talk now. And now I want to talk about how to do inference in this metalanguage, and I'll start with an example. And I'm using my example from before, but I want to apply it to a simple regression problem. So we have these data points, and we want to kind of find a line that goes through them, except that often in this kind of Bayesian probability setting, we're not interested in just one line that goes through all the points exactly. We're interested in a distribution on functions such that when we sample from it, it's a pretty good line, I should say. Okay, so if we naively just use our model from the previous, from a few slides ago, we're going to get a bad function on average, something like this. And if we want to improve this, what we do is, within each execution, we're going to reweight the execution in such a way that the good functions have a high weight and the bad functions have a low weight. And for this, we use this primitive called score, which is standard in probabilistic programming. It's sometimes called observe or factor. And what it does is it just reweights, so the execution just keeps track of a weight, and score just multiplies the current weight by some value, some real number value. And here we're saying something like, well, we have these data points, and we want to say for a given f that we've sampled, how close the line is to the point. So we're using a normal distribution to say if the point is close to the line. We're using the density of the normal distribution. Say if the point is close to the line, it should have high weight, and if it's far away, it should have low weight. And then the inference engine of the probabilistic programming language will look for samples with high weight, and by getting lots of samples with high weight, we're going to get an estimation of the posterior distribution, which is what we're looking for. So it might look something like this. We got this from LazyPPL. And so you can see that it's not just, they're not all perfect, and more importantly, there's not just one line, but we get a distribution on lines. I keep saying line, it's not actually a line. Right, so the metalanguage, we've now added the measures monad. And this measures monad, so we have everything from before, and now we have more operations. So the measures monad has 2 operations. You can sample from a probability distribution. And this sample operation is just saying, it should be a monad morphism. It's saying, it's just the fact that every probability distribution is just is in particular a measure. And the second operation is score, which just takes a positive real number and returns nothing. It just reweights the current trace. And that should still be commutative. That should always be true in probabilistic programming. And it should not be affine, because if it was affine, then we could just always delete the score, because the score doesn't return anything anyway. Oh, and this is also justified by the categorical story, because if you look at a one-point space and you look at the measures on it, that's not a one-point space. Okay, now I'll explain the denotational semantics of this metalanguage. So this is based on quasi-Borel spaces. That's a notion introduced in 2017 by people like Hong Sok and Sam, Ohad, and Chris. And so it's a category of spaces, generalized measurable spaces with very good properties. And the first thing before I explain this, I have to fix a source of randomness. So the main ingredient is a probability space. That's a standard Borel probability space, a space with a measure, a probability measure. And what I should be able to do is sample uniformly from that space. And the second thing is that I should be able to split any kind of random seed into 2 random seeds, because I always need to do that to produce more than one sample. And that should be measure preserving. Okay, now I've done this. A quasi-Borel space is a set equipped with a subset of functions from the random space into X. You can think of these as random variables with values in X. And so these spaces have very good properties. They form a category which is Cartesian closed. So we can, in particular, interpret the whole language with function spaces and so on. And moreover, it supports two monads, a probability monad and a measures monad. The probability monad is defined for a space X as the set of functions from the sample space into X, quotiented by some distribution. Yes, fine. Okay, thanks. Oh. Right. Yeah, thanks. So the probability monad on quasi-Borel spaces says for every X, we look at the set of functions from omega into X, and that represents a measure because we can always push forward, at least informally, we can push forward the probability measure on omega to a measure on X. And that should be quotiented because sometimes random variables give the same measure. Okay, and then I think, so I said quasi-Borel spaces are Cartesian closed category. That's very well known, but I think it's less well known that they also have this good property that measurable spaces don't have, is that they support a monad of measures, which is commutative and non-affine. So a measure on quasi-Borel space is defined to be a probability measure with a reweighting function up to some quotient as well that says two of these are the same if they define the same measure informally. Right, so we have these two monads, and so it's obvious how to interpret the metalanguage. Right, and so from this semantics, we designed the implementation in Haskell. So we have to say what omega is. We define this space tree, which is supposed to represent each tree. It's supposed to represent a random seed. And remember, you have to be able to sample a uniform distribution and a uniform value, and you have to be able to split the random seed into two random seeds. So kind of canonical construction is to take these infinitely wide, infinitely deep trees, and then fill each node with a uniform sample. So once we've done that, we've got our space of random seed, and given a what should I say the next thing? So now, we can split it by just allocating one branch to one bit of the computation, but that's because they're infinitely wide and infinitely deep. It's isomorphic to just having a tree. So we then have two trees. Okay. Right, and so omega is just tree, and now a probability distribution on A should just be a function, just like this here, should just be a function that takes a random seed and gives back, using the randomness in the tree, gives back a value in A. Right, and to get a measures monad, we start from the probability monad, and we sort of want to add this weight, so we use the writer transformer, a monad transformer that just sort of takes a monad and turns it into another monad that keeps track of a weight. Right, and an important point is that the bind of the probability monad is really using the splitting function. We allocate to each bit of the computation, we allocate a branch of the tree. We implemented this in Haskell, I said this, so we have this LazyPPL package or library that's available on that website. And one contribution that I didn't really talk about, and I won't have time to talk about, is that we implemented an inference algorithm, actually two inference algorithms to operate on these trees. So in Monte Carlo inference for probabilistic programming, you have to essentially define a Markov chain or a random walk on the space of random trees. So we have to say, given a tree, how do I produce a new tree? And we have to do this in a way that makes sense, but it's a bit difficult because the trees are lazy, and we want to go into the tree, modify certain values, and so on. So we have two different new algorithms. One that sort of modifies every node in the tree with a fixed probability, lazily. And the second one has to go into the GHC internals, look at how many, so basically hack the laziness away, look at how many trees have been computed. In Haskell, it's a bit hard to see what's actually been evaluated because it's all implicitly lazy. But so the second one is a bit more of a hacked algorithm, but it works well in some settings. So this is all in the paper. And LazyPPL has a few more features that I'll talk about now. One is stochastic memorization. So that's a primitive of this type. It takes a function from A to prob B, returns a distribution on functions from A to B. It's just standard memorization, if you know what that is. But in probabilistic setting, it actually changes the semantics. So the one way to understand it is, imagine A is the reals or some indexing set. This argument here is a kind of index family of random variables. And then this function is kind of saying, well, we sample them all at once to get a function that then, for any A, will give us a value B. But then, once we've got that thing, it's an actual function from A to B, so that will be deterministic. And the difficulty, of course, is that we can't sample them all at once if A is an infinite set. Right, so in Haskell, this is not immediately definable in the metalanguage. So in Haskell, we use some amount of state, which we hide so that it still fits within the probability monad. But it should always be safe, although there are some challenges for the semantics of memorization. And by safe, I mean that it should still satisfy the equations. Okay, so just a couple more examples. So in the language, we can define Gaussian processes that are really a fundamental model in probability theory. They're just random continuous functions that we can use for regressions as well. They have this type. And finally, another one is the Dirichlet process, which is random distribution. So it's in prob of A. And it happens to always be discrete. And just in 10 seconds, we have this unit interval that we break off into countably many pieces. So this is the lazy process as well. And then each interval gives us a probability coefficient for being in a particular cluster. If we're trying to do clustering, you can use it for other things as well. So it's a random, discrete probability distribution where both the weights and the atoms of the discrete distributions are sampled in a random way. Okay, yeah, this is all I wanted to say. So this is just a summary of the key idea. Yeah, thank you.
Thank you so much. We have some time for some questions. Any questions from the audience? Yes. Please introduce yourself.
So I'm Hong Seok, and I'm from KAIST. And have you thought about, developing some variational inference algorithms or Hamiltonian Monte Carlo in your setup?
Yeah, no, we haven't. I think maybe a HMC would be more easier than variational inference, from what I can tell. But of course, then you'd have to incorporate some AG or something in Haskell. And there are some packages, and I think maybe a student was working on that, but yeah, we haven't seriously looked into it. And via variational inference, I don't think we've looked into it at all. But yeah, I'd be interested to chat.
Go ahead. Turn it on.
Hello. Oh. Hi, I'm Jesse from MIT. I'm curious what the relationship is between laziness and streaming PPLs. I know there's a line of research on that.
What's the second thing, sorry?
Streaming probabilistic programming languages.
Streaming?
Yeah, that work on streaming data.
You mean like reactive or something?
Yeah. I'm curious if there's some relationship here.
Yeah, I don't really know. I don't know. It's a good point. I mean, it's a good point. Probably there are connections. Yeah, I'm not sure. Thanks. Yeah.
I think for streaming ones, you have to keep a fixed window for the reactive one. You want to keep a fixed window as you go through the stream, whereas laziness you keep all of them, right?
Yeah, exactly.
So that's that might be one difference.
Yeah, maybe. Yeah, thanks.
One more quick question.
Hi, Kenny from Charles River Analytics. I'm just curious if you've done any of this additional analysis or meta-analysis on PPLs in other languages. I see you've really spanned the Haskell community here, but personally as a user of PPLs, you got all kinds of stuff in the Python community, Julia community, the Scala community, and I'm wondering if what you see in terms of support for things like lazy inference and what have you. Just want to hear your thoughts on that.
Yeah, it's very interesting. So these other Haskell libraries are not fully lazy because even though they're in Haskell, there are some new ideas here to deal with the laziness, for example, like the tree idea and so on. But there certainly are ideas related to memorization and laziness in other older languages, like Church and Web People. As for all as you say, like Python-based languages and so on, yes, I'm not entirely sure. I think then you really go beyond this kind of meta language because you have state and you have a lot more things. So then,
Great. Well, let's thank Hugo once more.